Uh, our project for neural network course is to generate 3D images from 2D images using deep learning framework. Our group number is 121. Our team members are Sanjana Dalal, Shivang Patel, and myself, Priya Gandhi. Our motivation behind this project is that these days, in virtual reality, augmented reality, robotics, gaming, and in medical imaging as well, generation of 3D images is very crucial. And a part where we can generate 3D representations from 2D images is a fundamental problem. To solve this particular problem, we are using deep learning, which offers a fast, scalable solution by inferring depth and 3D geometry from one or several 2D images. For this, we have single RGB image as an input, which produces 3D depth map or mesh, enabling real-time application in a variety of fields. The dataset that we have used is NYU Depth V2 dataset, and it contains RGB images paired with depth maps. We have total 50,000 RGB depth images pair. Further details on the data and model would be explained by my teammates. Over to you, Sanjana.
The input are RGB images, and the output of the input is going to be depth maps. So depth maps are basically grayscale images that represent depth information. Depth map represents relative distance of each pixel from camera position. Darker the pixel means it's nearer from the camera, and lighter the pixel, it is further from the camera. Um, few of the data preprocessing techniques that we've used is image resizing and normalization. We've resized the images to a fixed size of 256 by 256 to ensure uniform input dimensions. And we've normalized the pixel values to a range of 0 to 1. We've convert the data to tensors. We've done so because uh, when you convert an image or depth map to PyTorch tensors, it uh, helps in computational efficiency and it's better for GPU compatibility. And we've split the data to maintain an appropriate ratio where the data is split into 80% training, 10% validation, and 10% testing.
So I would briefly explain the model building for our project. We have built on the intuition of using an autoencoder decoder pair for the project of converting the images to three-dimensional constructions. So for the baseline model, what we have is that we have used a very basic autoencoder decoder pair, where we have to ensure that both the models have the same number of layers and they build on the same number of neurons in each layer as well. So for the encoder part, we have used 5 layers, and for the decoder part also we have used 5 layers. And we can see that we have used two-dimensional convolutional neural networks, and for the decoder part, we have used two-dimensional convolutional transpose layers, so that we have to build on the information that we have condensed in the encoder part. So this was the intuition on which we built the model. And for the final part of the project, we have used transfer learning models as they provide better accuracy for image processing tasks. So for the encoder part, we have used the ResNet 50 model, in which we have not tuned the parameters given by the model. We haven't used any weights or we haven't modified the weights or biases for this model. However, for the decoder part, we have used the unit transfer learning model. And in this part, we have used the last 5 layers of this model, where we have fine-tuned the weights and biases based on the nature of our data set for the RGB images. And what we have built on is that the encoder would compress the information that is present in the two-dimensional RGB images, and the information would be presented in the form of compact latent representation. And When the information would be compacted, we take into consideration many of the features like the edges, the color discontinuity in the images, which are very, very essential when we are going to build the 3D output for the model. And we also take into consideration factors like noise or any irrelevant details which would be present in the image. So we have built on this model and we have achieved this result for our for our model. The graph that you see on the left represents the loss versus iteration graph for the baseline model, and the graph on the right represents the uh, loss versus epochs presentation for the transfer learning model. What we can see that the baseline model starts with loss value of zero 0.45 approximately, whereas the transfer learning model starts with a loss value of 0.24, which suggests that the transfer learning model starts with more performance and more accuracy compared to the baseline model. These values that we see, validation loss, validation accuracy, absolute error, and root mean square error, these are the values for the transfer learning model. And apart from that, these are the references that we have used. We have taken the help of the NYU-DEF dataset, which was present on Kaggle. And what future work we are planning to do for this project is that we can include more complex transfer learning models in order to capture more generic information from these images so that we can generalize the model for variety of different input images. Thank you, everyone.